Hi everyone. So welcome to the stream. And tonight I'm going to be doing, I think, 9 questions for both Physics 102 and 112, and 2 questions which are just going to be for the Physics 102 because they're calculus based. Okay, and we split the magnetism material into 2 weeks. There's quite a bit there, and especially for the Physics 102, and so we're doing the second half, and that's starting with flux. Okay, so we studied flux, the current induced by changes in flux, and then we studied a new electronic component called the inductor and what it does in circuits, like an LR circuit and an LC circuit. Okay, so we're going to do problems on that. All right, well, let's first start off with a very simple question. It's what does Faraday's law state? And there it is, stated as a formula. Okay, but I wanted to I asked this question because I really want people to think about it and have an intuition into what it's really saying. Okay, and basically what happens when you have a magnetic field, a wire in a magnetic field, okay, and the wire is not carrying a current. Actually, let's say a loop. You have a loop in a magnetic field, so that's a wire in a circular form or in some closed loop, and it's in a magnetic field, and the magnetic field is not changing at all. Then the loop is not moving or anything like that. Then there is no current induced in that wire. As soon as the magnetic field changes, or the better way to think about it is the amount of magnetic field lines which are trapped inside the loop. As soon as that changes, then you're going to get a current induced. And so basically that a measure of the amount of field lines that are enclosed within the loop, that is called the magnetic flux. Okay, that's what this word flux means in physics. It means trapped field lines. And if the field lines change for some reason, and the amount of field lines entrapped within the loop change, the rate at which they change actually gives you a voltage. Okay, and of course, as soon as there's a voltage in a wire, then there's going to be current through that wire. Okay, and that's what this says. V is the voltage that's induced in the wire. Okay, that's basically going to equal the change in the flux divided by the change in time. Now this is fine for our course, but technically speaking, this is for the Physics 102. This is actually a derivative. Okay, it's the rate of change of flux. Okay, it gives you the voltage. All right, in case there's some non-uniform variations, you'd actually have to differentiate the flux. Okay. So that's basically what it says. There's this negative sign there, which in our calculations we don't have to worry about. But it's basically Lenz's law. And Lenz's law says something like, I was going to ask it as a separate question, but I can get at it right here. Lenz's law says if the magnetic field is changing in one direction, then the current is set up such that it tries to oppose that change. It tries to create a magnetic field in the opposite direction to the direction in which the B field is changing. So it's the idea is something like the current is trying to stop the B field from changing. It can't, but it's trying to stop it. Okay, and so the current gets set up so as to try to oppose the change in the magnetic field, and that's Lenz's law, which tells you the direction in which the current is induced in a closed loop. Okay, all right. Well, that's enough for qualitative. Let's do our first problem here. What is the magnetic flux through a loop of wire with a radius of 5 centimeters placed in a 150 millitesla field such that the plane of the loop is at 55 degrees to the field lines? Now, what that 55 degrees to the field lines means is that if suppose the field lines are like this, okay, and the loop is like the plane of the loop is like that, okay, well then that would be perpendicular. 55 degrees would be something like that. Okay, so that's what we're going to calculate. All right, so let's do that problem. And there's the formula for the flux. So the flux is going to equal B, which is going to be 150 milliteslas, but we got to convert that to Teslas, 0.15 Teslas like that, multiplied by A, which is the area. And you know what, before we plug in, maybe we should calculate A. A is going to equal pi r squared, okay, like that, because it's a circular loop. Okay, I guess I said a loop of wire with radius. I guess it's understood that when you say radius, you mean a circular. Okay, loop. Okay, so it's 3.14 for pi and 5 centimeters, but in MKS 0.05. squared like that. And let me see what that area turns out to be. It turns out to be this, okay? And that's in meters squared. And so that's the number we're going to plug in right here, okay? And then sine of, and that angle theta is the 55 degrees. It is the angle that the plane of the loop makes with the B field. So 55 degrees like this. All right, and what's that going to equal? I'll tell you in a second. Actually, let me rewrite it without the units in there so I can cut and paste this into my calculator. Oh, it doesn't like the sign. Okay. It still doesn't like it. 1 second. Oh, I don't know what it's not liking. There we go. Okay. Copy. And so that's going to equal this number right here. Okay. Too many digits, so we'll want to only keep up to these last three significant figures here. So that'll round off to this. Okay. And the units are Teslas, meters squared. Okay. Now that's really ugly to have that many decimals in front, so we'll actually move the decimals over 3. 1, 2, 3, and so we're going to have 0.9 like that milliteslas. Okay, and I sometimes put a little dot in there just to show you that, whoops, just to show you that this part is the millitesla part and that's the meter squared part. Okay, and so there you go, that's the flux through that loop of wire. Okay, so let's read the question again. See that we answered it. What's the magnetic flux through a loop of wire of radius 5 centimeters placed in a 150 millitesla field such that the plane of the loop is 55 degrees to the field lines? Okay, and so the answer is close to 1 millitesla per millitesla meter squared. Okay, now here's the next part. And the next part here, question number 3, actually gets into Faraday's law, okay? Because we're going to turn the loop. Now, when I was talking earlier, I said, the entrapped field lines. Well, the field lines are going through the loop like this. I mean, if I turn the loop like that from from plane like that, or I guess it's at 55 degrees to 30 degrees, the number of field lines are going to change because the loop is more parallel now to the B field. Okay, and so when that changes, when the flux changes in there, it's going to change over a certain amount of time. I said over 15 milliseconds, and so that it's going to induce a voltage. Okay, so if we turn the loop from 55 degrees to 35 degrees in 15 milliseconds, what voltage is induced in the loop? Okay, so take a look at the Faraday's law again. There's the delta phi, and that would be the delta phi from before and after. So before, we already have that because we calculated that at 55 degrees. The after is going to be the same, but calculated now at 30 degrees, okay? Or sorry, 35 degrees, okay? So here we have this value here, all right, is equal to this. And we can call that the before, the flux before the turn. And you say, well, what's the flux after? So we're going to have the same thing, but now we're going to calculate it after, like that. Well, it's the same formula. Well, let me grab this formula from here. It's the same formula. So plugging in the numbers, the field intensity stays the same. The area of the loop stays the same. We didn't deform the loop, but now it's going to change from 55 degrees to 35 degrees. Okay, and so let me see what that flux is equal to. And it still doesn't like what I'm doing here, so let's try this again. All right, there we go. All right, so we get this number here. So lots of digits again. So we'll just remove everything but the last 3 digits and the same units like that. Okay. All right. So that's the after. All right. So now let's look at what the change in flux is going to be. So there's the delta phi. Okay. And don't worry about that negative sign because, again, that's about the direction, and the question is just the voltage and not the direction. Okay, so when we do delta phi, it's going to be the before minus the after. All right, so I'll just put in the numbers directly. So it's going to be this number here. minus that number there. Okay. Whoops. I put a millitesla there. There it is in Teslas, and then in milliteslas, and I have to scroll that down so you can see it. So in milliteslas, it'll be that number, but with the decimal moved over 3 like that. Okay. So there we go. There it is in milliteslas. Okay. And let me cut that, paste that over here. You see if you can see that. Yeah, you can. Okay. And so what's that going to equal? So delta phi is going to equal this number minus that number. Okay, let me put that in my calculator. All right, it's going to equal, you know what, I'll just do it this way. Millitesla meters squared. Okay, so there's your change in flux. Your change in flux is going to be about 0.3, 0.29, 0.290. Actually, we have the one more significant figure there, 0.290 millitesla meter squared. Okay, so there's your change in flux. How long does it take to do that? Well, that's your delta T, and there's delta T there like that. I just tell it to you directly. I said it's 15 milliseconds. Okay, so the only thing tricky here is that it's in milliseconds, and that means move the decimal over 3, so 0.015 seconds. Okay, so right, that would be milli. Then 1, 2, 3, and then there it is in seconds. Okay, and then just copy this over here like that. And if we're just worried about the magnitude, again, don't worry about that negative sign. So you know, we're not worried about the direction of the volt. Like, we're not worried about which side is positive and negative. Okay, it's just going to be this number here. Divided by, actually, you know what? I didn't even have to convert this to seconds. I could just divide by 15 milliseconds. Okay, and I'll show you why. Because, see that milli right there? I'm going to put some brackets around this. It's a little easier to read. Okay. And put some brackets around this. All right. Okay. So you see that milli there and that milli there? The two millis cancel because both of them are 10 to the minus 3. So that's going to cancel this one like that. Okay. And then let me just pull the units outside. That's going to be a Tesla meter squared there divided by a second there like that. Okay, and you say, what the heck is a Tesla meter squared per second? And it turns out that a Tesla meter squared per second is a volt. That's exactly what a volt is. And so the voltage in the loop is going to be this number here, which I'll calculate. All right, like that. And a Tesla meter squared second, that is a volt. Okay, now again, let's move the decimal over 3. 1, 2, 3. Okay, so that'll give me 100 and no, it'll give me, let's see, 1, 2, 3. It'll give me 19.3 millivolts. All right, and there's your answer. Okay, so 19.3 millivolts. All right. Let me just quickly say what I did there. I'll go over it again and take a look if there's any questions in the chat. All right, so you know, if we turn the loop from 55 to 35 degrees, then there's going to be a change in the flux. Okay, and that change in flux is going to happen over 50 milliseconds. If you have a change in flux over some time, that's an induced voltage. Okay, now if you take a look here, that's this formula right here. So, whoops, went too fast. That's Faraday's law right there. Okay, change in flux divided by the change in time. The change in flux, there was a flux before, which we calculated in question 2. There was a flux after, which we calculated in the same way that we did question 2. The change in flux is just the difference between the two. Okay, divide that by 15 milliseconds. So the change in flux divided by 15 milliseconds, okay, gives us 19.3 millivolts. Okay, so you know, in turning that loop from 55 to 35 degrees, you know, there's a slight change in flux. We did it in 50 milliseconds, so we got 19.3 millivolts. Okay, let me take a look here in the chat and see if there's any questions. Well, we have some viewers, and I don't see any complaints about my audio, which is good. So it looks like you can hear me. And what got me really worried last time was that I was seeing the audio levels okay on my end here, but people weren't hearing me, and it had something to do with the way my earphones had been slightly disconnected. But anyway, okay. Anyhow, all right. So there you go. There's the story with flux. By the way, before I move on, flux is how, or changing in flux, Faraday's law is basically how electric generators work. If you change an electric field, sorry, if you change a magnetic field in a loop of wire, or more than one loop of wire, many loops like a solenoid, and you're changing a magnetic field in there, then you're going to induce a current, okay? And that's exactly what's happening at the power plant in like Lewiston, New York, or on the Canadian side. And what's happening is as the water goes down a chute, it turns these turbines, okay, which is basically just like propellers, but for water, okay, it turns these turbines, and they move magnets. They move these magnets in and out of coils, and as the flux changes in these coils of wire, a current is induced, and that's how we make electricity, okay? And by the way, it's one of the cleanest forms of electricity. If there was just more water that we could harness for this, we would have some of the cleanest energy in the world, because, I mean, I guess there's always a little bit of pollution, but compared to the other forms of energy that we use, like, coal or fuel, or, fossil fuels, I mean, it's extremely clean. So that's kind of nice, if we could just do some more hydroelectric, and that is where water going downhill turns turbines, which moves magnets, which changes fluxes in coils, and then induces a current. Okay, let's move on. So the next thing we studied was inductance, okay? And the device which exhibits inductance is called an inductor, okay? So what is it? What is this thing? What is an inductor? Okay, well, let me remind you about some of the other electronic components that we discussed, okay? We discussed a resistor, and what a resistor does is it resists current, okay? So if you put a potential across a resistor, you'll only get so much current, because the resistor is trying to stop the current from going through, okay? You have to put more potential to get more current through the resistor, okay? And that was Ohm's law. A capacitor is a device which just simply stores charge. So if you put a potential across a capacitor, then one plate becomes positively charged, the other one becomes negatively charged. The more potential you put across that capacitor, the more charge is accumulated on the capacitor, okay? And then there is an inductor, and the inductor is probably the hardest of them to understand. So, if you've got a circuit and there's a current moving through the circuit, if there's no resistance, that's like no friction. The current will just keep moving at the same speed, okay? What an inductor does is it because it's like a solenoid, it builds up a magnetic field which keeps that current going. And then if you try to stop or start the current, like if you try to increase the current or decrease the current, it resists changes in the current. It doesn't resist the current the way a resistor does. It resists changes in the current. So you might have a current through an inductor of 1 amp. And the inductor is saying, I'm happy with this 1 amp going through here. So it's not resisting the current. But if you try to change that 1 amp to 1.1 amp, the inductor is going to go, no, I don't want you to do that. You're going to have to give me some energy. You're going to have to put some energy in order to increase that current, okay? So it's not so much that it's resisting the current. It's happy to have the current there. It's resisting changes in the current. Okay, so as long as it's that 1 amp current going through the inductor is happy. But as soon as you try to increase it to say 1.1 amps, or you try to decrease it to 0.9 amps, well, then there's some energy involved with that, because the inductor is resisting the change. Okay, so a little bit more subtle, but that's it. So that's why I asked this question. I wanted to make sure that people understand intuitively what an inductor does in a circuit. And again, it resists changes in current. Okay, so let's do some problems here. Okay, so the first one, I don't think I asked the question like this in the assignment, but I could, on the test and whatever, and I could have on the assignment. But this one, it goes at the definition of inductance. Okay, and so a minute ago I said, to change your current going through the inductor, you're going to need some energy. And whenever you're talking about energy or energy per unit charge, you're talking voltage. And so this is actually the definition of inductance. Okay, L is actually the inductance there, but usually you write it in this form right here. because it's easy to see what inductance is balancing. Okay, so L is the inductance, and it has units of Henry in MKS. Okay, and on the one side you have delta I over delta T, and you say, what is that? Delta I is your change in current. So like in my example a minute ago, going from 1 amp to 1.1 amp, the change in current would be 0.1 amp, because it's going, 1.1 minus 1 is 0.1. So that's your delta I. That would be the change in current from before and after. The delta T is how fast you make that change. Okay, so the faster you try to change the current, the harder the inductor is going to try to resist that. Okay, and L is the inductance there, and that change in current, the rate of change in current, that's going to cost you some voltage in order to do that. You're going to have to apply some voltage in order to get that change, and the inductor is the equivalence, or the conversion between how quickly you want to change the current and how much potential you have to put on it to do that. Okay, now if you have a very, very big inductor, it really resists changes in currents, and so you're going to need a lot of voltage. V is going to be very big, even for a very small rate of change in current. Okay, why? Because L is big. So if L is big, this could be small. The rate at which the current is changed could be small, but because L is big, you're going to need a lot of voltage. A very small inductor is the other way around. Okay, if you want to change a very big, rapid change in current, well, if L is very small, well, then you only need a little bit of voltage to do that. Okay, because there's not much inductance resisting that change. Okay, so there's the definition. All right, so here's a question to try to make use of that definition. A current through an inductor induces an average voltage of 7 volts. I don't know if I wrote this right. A current through an inductor induces an average 7.5 potential. Nah, I didn't write it right. Okay. A current through a inductor requires, S is a better way to write, requires a 7.5, let's get rid of the word average. I know why I put it in there, but this will read better. Okay, a current through an inductor requires a 7.5 voltage potential to change a current from 150 milliamps to 100 milliamps in 9 microseconds. What is the inductance of the inductor? Okay, that reads a lot better. Sorry about that. I should have reread my own question. Okay, so a current through an inductor requires 7.5 volts to change the current from 150 milliamps to 100 down to 100 amps. So 150 milliamps down to 100 milliamps in 9 microseconds. Okay, what is the inductance of the inductor? Okay, so let's go through it. The current is changed. Let's start on the right hand side here. So we have delta I over delta T. What's your delta I? All right, so your delta I is your change in current. Okay, and you start at 150 milliamps. And I guess you want to do it the other way around, but you know what? It doesn't really matter, because we're not worried that much about the we're not that worried about the sign. So you know what? I'll even put this in absolute values just to indicate that I don't care about the sign. The sign, again, is just this business of what direction the voltage would have to be in. Okay, so it'd have to be one way if you try to increase the current. It'd be the other way if you wanted to decrease the current, but I'm not really worried about the direction here. Okay, so usually what you do when you do a delta change, it's the after minus the before, sorry, the before minus the after. I did have it right the other way, but it doesn't really matter like which way we're subtracting. Okay, because we don't care about the sign. Okay, so 150 minus 100, that's 50 milliamps. Okay, so there's your change in current. It's 50 milliamps. How long does it take to do that? Well, it's delta T. Let me delta T right here. Okay, delta T is equal to 9 microseconds, like that. Now micro and milli, what are they? So milli is 10 to the minus 6. Maybe we should write that here. 50 times 10 to the negative 6 amps, like that. Okay, and micro, milli is 10 to the minus 3, and micro is 10 to the minus 6. So this will be 9 times 10 to the negative 6 seconds. Okay, so there we go. We've got it in MKS units. Okay, and the voltage was 7.5 volts. So if we take this formula here, we can plug in. Actually, before we plug in, let's just calculate this piece. Okay, so I'll make it a little easier. So we have the change in current, 50 times 10 to the minus 3, divided by, let's get rid of the amps because it's already an MKS, we don't need the units in there, divided by the time, like that, 9 times 10 to the minus 6, and that's going to give us, all right, it's going to give us this number right here. Okay, and that's amps per second. Okay, and well, we should probably round that off to 3 significant figures, so it'll be 5560 amps per second. Okay, so that's the rate of change. Okay, 5,560 amps per second. That sounds like a lot, and because 5,000 amps is huge. Okay, that's like lightning level. But don't forget, this is happening over microsecond ranges. Okay, so it's not that. It's over a very short period of time. Okay, and now we can take this formula here. Okay, and V I said was 7.5 volts is equal to L, which we're trying to solve for because I'm asking for the inductance L. And then there's that right there, the rate of change of the current. Okay, so L is going to equal 7.5 divided by 5560, like that. And what's that going to equal? That will equal this number right here. Okay, now what are the units? The units for inductance in MKS are henries, okay, named after a physicist, Henry. Okay, so there it is, like that. And on a test, you probably would not see it that way because I would move the decimal over to 3. 1, 2, 3. So 1.35 millihenries. Okay, and this is not an atypical number for an inductor. Okay, it's a good size inductor, you know, but you know, you can easily make an inductor of that size in the lab. Okay, so there you go, and this is just directly using the definition of inductance. Okay, so let's just look at it one more time. You've got a current. The current is going to change through the inductor in a certain amount of time, and it takes so much voltage to do that. What's the inductance? Okay, so the current changes, that's your delta I. In a certain amount of time, that's your delta T. Okay, and it takes so much voltage to do it. There's your V. We calculated L. All right, great. I take a look if there's any questions in the chat. And okay, good. And I'm going to take a sip of my coffee, so I'm going to just momentarily mute my. There you go. All right. So great. Now, how do you make an inductor? Like, what's it made out of? Like, you remember resistors are basically materials that have a lot of impurities in them, which cause friction as the electrons flow around them. Capacitors are just two parallel plates. Okay, and what's an inductor? How do you make an inductor? Well, a solenoid is a perfectly good inductor. Okay, and so I derived for you in the lecture the formula for the inductance of a solenoid, and it depends on a few things. First, whether or not it has a core, a ferromagnetic core. Okay, and this formula that I gave here actually is the one without the ferromagnetic core. But if there is a ferromagnetic core, maybe I should just show you that very briefly. If there was a ferromagnetic core, then you'd have to multiply by the relative permeability. So let me just write this in because this is the more complete formula here. So first, you know, is there a ferromagnetic core, and what's the relative permeability? That's your mu r. Mu naught is just that permeability of free space, okay, and it's just a constant, okay. It depends on the number of windings, n, and it actually comes in as n squared, and that's because each loop is actually inducing it's producing a magnetic field and inducing a current in another loop. Okay, so it's like loop interaction. If there's n loops and all n of those loops are interacting with all n other of those loops, then that's why it comes in as n squared. It depends also on the area that's enclosed in any one of the loops, which makes sense because it's the flux, okay? And that's divided by L, which is the length of the solenoid. Okay, now in this particular situation, or in this particular question, I said let's look at the solenoid that we actually played with in the lab. Okay, and that solenoid did not have any ferromagnetic core. You could put something in there, but it had no ferromagnetic core, so we're just going to remove that mu r, okay, or the mu r is equal to 1 in that case. So this is the formula when there is no ferromagnetic core. Okay, it's just like an empty solenoid. All right, and so the lab, that solenoid that we played with in the lab, it had 570 windings of wire, okay, around it. You didn't have to count them. We told you that in the lab write-up. If you measured the length of the solenoid, it was 15.4 centimeters, okay? And the diameter, I don't actually know. I didn't measure, and I couldn't, I don't think it's in the lab handout. So this number I actually guessed. I just said 10 centimeters. It's probably less than that, but that's okay. This is good enough, okay? So what was the inductance of that solenoid in the lab, approximately, okay? Because I don't know the radius, okay? And so let's work it out. Well, let's start off with A, the area, and that's going to be pi r squared like that, and pi is 3.14. And I didn't want to be tricky, but I said diameter of 10 centimeters because that's the way I'm kind of thinking about this. If you were to measure it, it's hard to measure radius. It's easier to measure diameter because then you're going from side to side. Radius, like where's the center? Okay, so 10 centimeter diameter means a 5 centimeter radius, so 0.05. Okay, squared like that. And so the area enclosed by the solenoid loops is going to equal, actually this number came up just a minute ago because it's the same. Okay, so there we go, 0.00785 meters squared. All right, and so there's our A. N, well, I told you that N is 570. Okay, L is the 15.4. We're going to change that to meters. So 0.154 meters like this. Okay, and the mu naught is just a number, 1.26 times 10 to the negative 6, and the units are going to be Tesla meters squared per amp. Okay, and you can see that actually here. Well, no, you can't, not in this formula, but you can in the formula from last week, okay? But there you go. There's the formula for that, okay? By the way, a different way to write this, now that you should be pretty good with units, is remember 10 to the minus 6 is milli, okay? Oh, sorry, micro. And so you could take out the 10 to the minus 6 there, and you could just put in a little micro, if I can grab one from up here somewhere. There we go. Okay. And I just mentioned that in passing because you might see the number written this way, okay? So the permeability of free space, this is like the measure of the ability of, it's the inductance of free space. That's another way to think about it. It's like the inductance of free space per unit length, okay? It's milliteslas multiplied by meters divided by divided by amps. Okay, that is correct. Okay, but it's in the microtesla range. All right, so 1.26 microteslas. All right, so we can actually use it like that and just make sure that we keep that micro because it's just like carrying the 10 to the minus 6 along. Okay, and so over here we've got this. So let's put in 1.26, and you know what? That's okay. Let's do it all in MKS. Yeah. All right, there we go. All right, so there's the micro, and 570 like that for the number of windings. The area, there it is like that. And the length, there it is like that. Okay. So there we go. Now this will come out in MKS, okay? I was going to work it out in microhenries, but that's okay. We'll just do it this way. All right, so L is going to equal this number here. That's what's coming out of my calculator, but we only want 3 significant figures, so there they are. Okay, so get rid of that. Notice that's a 6, so that would be 9 there like that. Henries. Okay, and move the decimal over 3 to get it into millihenries. So 1, 2, 3. So this would be 20.9 millihenries. Okay, so there you go. That solenoid that we had in the lab is 20.9 millihenries inductance, okay, which is fairly big, okay, but not that big. Let me actually add another part to this question just to show you. Suppose that we did add some kind of ferromagnetic core, and something like a nickel ferrite, I think, has a relative permeability of 2,300, like that. Okay, well, in that case, your inductance would be the same number, millihenries, okay, but the ferromagnetic core, all it does is it just enhances it. So that means it's just like multiplying by 2,300, like that. Okay, so let's say repeat with a ferrite core with relative permeability of 2,300, like that. Okay, and now this number is going to equal, multiply it by 2,300, whoops, it's going to equal 48 henries. Okay, this is huge. All right, so that's really big. So adding those metal cores are pretty big. By the way, if you want to see an inductor, if you ever take a look, like if you have a computer that you can see inside, most of you have laptops which you can't open up, but if you have a computer that you can see inside, you look on the motherboard and you'll see these coils of wires that look like solenoids, but in the middle of them there's like usually some kind of a black bar, and that black bar is usually some ferromagnetic material, because the presence of that ferromagnetic core greatly increases the inductance. Okay, so that answers that question. Let me just go over it again. It's very simple. It's just a matter of plugging in. Okay, so solenoids make great inductors, and the formula is just this. Okay, so you need the number of windings, the cross-sectional area, and the length of the solenoid. Then you multiply by the permeability of free space, and if there's a core, you also multiply by the relative permeability. Okay, so let me see if there's any questions in the chat. No, 3 viewers and no questions. And I'm going to just check my audio levels here for a second. I'm really paranoid about this. Oh, they're good. All right, let's move on. So question number 7. Okay, and let me just move this so it's a little easier to read these formulas. Okay, so whoops. Now, the questions I just did were like for an isolated inductor, but you can put inductors in circuits. You can put them in circuits with capacitors, and you can put them in circuits with resistors. Okay, and you can even have all 3 components, although we didn't do that. We didn't do an LRC circuit, but we did do an LR circuit. Okay, so an LR circuit is an inductor and a resistor in series. Okay, now remember what the inductor does. It kind of gives that current a steadiness to it. It tries to keep it at the level that it is. But what does the resistor do? It resists current, so it kind of bleeds away the energy. And so whenever you have an inductor and a resistor together, and there's a current already going, the resistor is going to bleed away the energy, but the inductor keeps pushing it, and so it bleeds away slowly. Okay, so that's when you get the exponential decay. In this particular problem, I hook it up. There's no current at first. I turn on the switch, and what does the inductor do? The inductor resists the change in current, and so it doesn't just jump up to a maximum current. It increases. It winds up over some time, and you get this characteristic exponential growth. Okay, well, not really exponential growth, but exponential growth to an asymptote. Okay, we'll look at the formula for that in a second. Okay, but let's read the problem first. Okay, so we hook up a 100-volt battery to a 375 millihenry inductor and a 15 kilo ohm resistor in series with a switch. Now the reason you need the switch there is because you don't want any current to start with. You close the switch, And as soon as you close the switch, the current starts to increase from 0 to a maximum. Okay, so let me actually say that. We close the switch and the current starts to increase from 0 to a max. Okay, to a maximum value. All right, so now I asked 3 questions. What is the maximum current that will be reached? Okay, so actually, before I jump in on those questions, here are the formulas that you need for that. First, this one is a situation where you start at 0 and you wind up. And in that case, you want this particular version of the formula, okay? If it was the other way around, if you were actually, started with a current and then you exponentially decayed, the formula would be this one. Now, let me write it over here. I'll get rid of it in a second because we don't need it. But this is the one, okay? That's the one where you start at some current and you decay down to 0. This is the so that's this one right here. Start with some current and decay down to 0. This one is where you start at 0 and wind up to some maximum value. Okay, and that's the situation we want. That's the situation we're in right now. Okay, so we start at 0 and wind up. As soon as we close that switch. Before we close the switch, we're at 0. And as soon as we close the switch, we're at 0. But then we start to wind up, and then we'll eventually get to a maximum. Okay, and this formula here that tells you the time constant, the characteristic time for the circuit to build up its current. Okay, and it's different than the RC circuit. There, tau is equal to RC. Here, tau is equal to L divided by R. Okay, and finally, maximum, that I naught, that's your maximum current. Okay, so I don't know why I wrote that in there, but just to remind you that I naught is the maximum current, and that's just V divided by R. And the reason is once the current gets to a maximum, it doesn't go any higher, it stays steady. And as soon as the current is steady, the inductor is like transparent. The inductor is like no longer doing anything. It's no longer resisting anything because the current isn't changing. Okay, and then it's just purely the battery and the resistor. Okay, so now we can answer those questions. All right. So the first question is, what is the maximum current that the circuit will reach? Well, that's easy. It's just this one right here. Okay, so the answer to question A is going to be V over R. I naught is equal to V over R. So V is 100 volts. And R is, 15 kilo ohms, but kilo is 1,000, so there we go. So it's going to be 100 volts divided by 15,000 ohms. And what's that going to equal? It's going to equal this number right here. Okay. All right, and so let me round it off to 3 significant figures like that. Okay, and it's a current, so the units are amps, but we want to make this look nice, so I naught is going to equal, move the decimal over 3, 1, 2, 3, 6.67 milliamps. Okay, and again, very typical numbers for a lab situation. So that's the maximum current you're going to get if you put an ammeter into the circuit and you just wait until the current winds up, gets to its maximum. It will not go over 6.67 milliamps. Okay, great. Now what? So the next question was B. What is the time constant of the circuit? Well, that one's again pretty easy. It's the last one, which gets a little harder because you got to work with the exponential. So it's going to equal L over R. L is, I'll put it in, so I'll plug in with a non-MKS and then we'll convert, divided by 15 kilo ohms like this. All right, but that's not MKS. So over here, milli. So move the decimal to the left 3, 1, 2, 3. So that's going to be 0.375 divided by 15 kilo is 1,000, so it's 15,000. So it's a pretty small number. Okay. And it's going to be this number right here. All right, and that's in seconds, but that's a terrible way to report a number. Okay, so move the decimal over 1, 2, 3, 4, 5, 6. Okay, so if we move it over 6, that's going to be 20 5. And because we moved it over 6, that is micro. So let me get my micro up here. I had a micro somewhere up here. So I'm just doing a cut and paste. All right, let's go back. Okay, there you go, microseconds. Okay, so why micro? Micro is 10 to the minus 6. So, if you move your decimal over 6 to the right, then you're in the micro range. So there's the decimal. There's 1, 2, 3, 4, 5, 6. So 25 microseconds is the time constant for the circuit. Okay, now that's not something that humans can deal with, but if you remember from the labs that we've done, or lab I guess last week, with the oscilloscope, when you're triggering it, you can certainly measure down into the microsecond range. Okay, that's not too much of a problem for an oscilloscope. All right, so now what? Okay, so that answers part B. Now here's part C. What is the current at 1.5 taus? Okay, so what do I mean by that? Well, what I mean is, see, what is I when t is equal to 1.5 tau? Okay, so first of all, what's 1.5 taus? So t is equal to 1.5 times 25 microseconds. All right, and what's that going to equal? 25 multiplied by 1.5. It's like 37.5. Okay, 37.5 microseconds. So another way to have asked this question, okay, by the way, this is a typical way of thinking about it, like thinking in terms of units of tau. All right, so 1.5 taus. But another way to ask that question would have been this. Let me just cut and paste it here. Rather than asking it this way, what is the current at 37.5 milliseconds? Okay. All right. You say, well, how do you solve that? Well, for this, you have to go back to the exponential decay formula. Okay. So let's look at it one more time. Here we have t, and that's the time at which we're interested in. And we've already determined that that's at 37.5 microseconds. Okay, so that t there is going to be the 37.5 microseconds. Tau is just a constant because for a particular circuit, because L doesn't change and R doesn't change, so it's just that 25 microseconds. So that's constant. Okay, I naught is the maximum, and I'm asking you, what is I at that particular time? So we want I. So I is going to equal, the current is going to equal, cap locks. I is going to equal I naught. Okay, and we determined that that was 6.67 milliamps. 1 minus the exponential of negative, the time is that we're interested in is negative 37.5 microseconds, like that, divided by, let me just put some space in there so it's a little easier to see. Okay, divided by the 25 microseconds in the denominator there, like that. Okay, and there you go. Okay, so I've plugged in the units. Now I space things out a lot here on purpose. Okay, so you see that the 37.5 is in microseconds, so t is in microseconds, and the tau is in microseconds, and t divided by tau, as long as they're both in the same units, the units will drop out and that'll be okay. So there the microseconds will cancel against microseconds there, like that. And now we can just plug into our calculator and do this. And so let me just rewrite this without the units so that I can cut and paste into my calculator. This should be able to do that. Oh, I didn't like that. Okay. There we go. All right. So I get that I is equal to this number here, but too many digits again, so we'll just round it off to 3. And notice that I had milliamps there, so this is going to be milliamps, and so my answer will come out in milliamps as well. Okay, and so there you go. After 37.5 microseconds, the current is at 5.18 milliamps, but it will continue to increase to what? To 6.67 milliamps. Okay, so we're not quite there yet. We've reached, after 37.5 microseconds, we've reached 5.18 milliamps, but we can still grow a little bit more. We can grow up to 67.7 milliamps, but you can't go any higher than that. Okay, so there you go. There's that question for an LR circuit. Let me see if there's any comments, questions in the chat. Nope. All right. So let's move on then if there's no questions there. All right. So the next circuit and the last circuit we studied was an LC circuit. And this is now an inductor and a capacitor in series. And I said to you, in this question, I'm just asking, describe what how the current varies over time in an LC circuit. Okay. And to really understand this, you should watch, of course, the lecture, or maybe even read the notes. It's a little bit demanding conceptually, but basically what happens is imagine that the capacitor is charged up and there's no current right now in the circuit or through the inductor. Okay, so then what does the capacitor want to do? Well, the capacitor sees a path for the positives to flow to the negative. Okay, but it goes through the inductor. Remember, the inductor resists the change in current. So what happens is the capacitor, as it starts to push its charge through, the inductor says, no, not so fast. So it takes some time for that capacitor to begin to get the current flowing to the other side. Now the thing is that once that current is built up, the inductor says, look, I'm not going to stop this current. This current's going to continue going. So even when the capacitor is discharged, the inductor keeps pushing. So one plate, the plate that was positive, now pushes all of its, the other plate not only goes neutral, start with the plate that's negative. Not only does it go neutral, but the inductor keeps pushing and now it becomes positive, and the plate that was positive now becomes negative. And then the whole process occurs again, but in the other direction. And so what you get is this oscillation where the current flows one way, and then it turns around, flows back, and then it turns around and flows back. So the capacitor is pushing it one way, but then the inductor keeps it going even after the capacitor is discharged, and it charges it back up, but with the opposite polarity. And it does this back and forth, and it's basically oscillation. And this is how you make a radio transmitter or even a radio receiver. That's basically a tiny radio. Okay, an LC circuit is a tiny radio. Okay, either a radio transmitter or a radio receiver, depending on whether you drive the circuit or whether you're using the circuit to pick up resonances from some other radio source. Okay, this is kind of interesting. Okay, so in answer to the question, if you just say, well, how would I briefly answer the question? What is the how does the current vary over time in an LC circuit? It oscillates back and forth. Okay, that's it. It's an oscillator. So how a pendulum will swing back and forth like that. This is the electrical equivalent of an oscillator, where the current will flow one way and then it'll turn around, flow the other way, and then back and forth like that. Okay. All right. So there's a frequency associated with that. So what is the linear frequency of an LC circuit made up with a 95 microfarad and a 25 millihenry inductor? Okay. So the formula for that is F is equal to, and you know what? Let me look it up how I wrote it, because sorry, I should have probably been ready for this, but let me just look it up how I wrote it, because I want to make sure that I did it right. Yeah, I should have looked at the formula beforehand. But see, there's two ways. One is in terms of the angular, and the other is in terms of the linear frequencies. I think I did both, actually. I think I did both. Why is this taking so forever to scroll? Oh, this is so weird. I'm sorry, guys. This is taking way longer to scroll than it should. It's probably because I'm using uh, a different browser here. Yeah, this is ridiculously slow. There it is. Okay. Did I write it correctly? I did. Good. Okay. So F is equal to 1 divided by all in the denominator 2 pi times the square root of L times C, like that. Okay. So there's the formula that you want to use for the frequency. All right. So basically, just plug into that and you get the frequency. Okay. But you got to, of course, be an MKS to get out hertz. Okay. So 1 divided by 2 times 3.14 times the square root of L. So there's the inductor, which is 25 millihenries, like that. Okay. Times C, which is the 95 microfarads, like that. Okay. All right. Now, this is not MKS right here. All right. So let's do that. Milli, the millihenry is 10 times 10 to the negative 3. Milli is 10 to the minus 3. The micro is 10 to the minus 6. Okay, so over here, we'll take that out. It's 10 to the negative 6. Okay, and there you go. This is now an MKS. All right, so let me see if I can calculate that. Is that going to work? It doesn't like something. What doesn't it like? Uh-oh. Yeah, I'm going to have to do this in... Oh, I see what it doesn't like. I see what it doesn't like. There we go. So 103 and then some decimals, so rounding off to just 3 decimal places like this. Hertz. Okay, there you go. So the frequency would be 103 hertz. Now 103 hertz is nowhere near radio, like our radio AM or FM radios. Okay, AM is in the kilohertz range, hundreds of kilohertz, and FM radios in the hundreds of well, the tens of megahertz. Okay, so it isn't there. This is a very, very low frequency. Okay, but you know, it's still, you know, something which is definitely measurable in the lab with an oscilloscope. 103 hertz. Okay, so there you go. And both of those sizes there, the 95 microfarads and the 25 millihenries, those are typical size capacitors and inductors that you would get in a lab. Okay, so let me see if there's any questions about that in the chat. And nope, there's no questions. Okay, so all right, so that covers all the topics for Physics 112. Okay, so if you're a Physics 112 student, that's it. You want to stop unless you want to go through the pain of calculus. You want to stop watching at this point. Okay, for the Physics 102 students, what I did is I actually proved some of these formulas. Okay, now you know, our tests are multiple choice, so you're not going to actually prove these formulas. But what I can do is I can ask you to derive formulas or related formulas from the formulas that we looked at because of the calculus behind it. Okay, it's not too hard, but you know, if you're not sure how to do this, you know, if you didn't study those notes, you're going to find this very difficult. Okay, but once you understand the principles, it's not that bad. Okay, so I asked a couple of questions like this on the assignment. I think those questions on the assignment were a little bit in the easy side, so these ones are a little bit maybe a little bit more demanding. Okay, so again, from this point on, this is just for the calc-based physics students. Okay, so let's start. All right, so over here, I said, what is the formula okay, for the charge on a capacitor in an RC circuit that is discharging, okay? Whoops, discharging, spell it right, okay? Now, in those notes, when I did the exponential decay, I only did exponential decay. So I only did the discharging. I did not do the charging. The charging is, or winding up of the current in an LR circuit. That's not that different, but it doesn't teach you anything new. So I just did the discharging, okay? And this one is a very easy, because you could just look it up. And there it is. There's the formula, okay? So the formula for the charge on a capacitor in an RC circuit is just equal to Q, and it's given by Q naught, okay, which is the maximum charge on that capacitor, I guess at t equals 0, multiplied by the exponential decay. And the exponential decay goes as e to the minus t divided by tau, where tau is equal to RC. The time constant for an RC circuit is equal to RC, okay? Now, that was easy. So you say, oh, no problem. Now, what if I asked you this? What is the formula for the current in an RC circuit when it is discharging? Okay, and now you go, whoa, I didn't give you that formula. Not directly, I didn't. You're right. You're not going to find that directly, but it's not that hard to get, because what's the relationship between the current in these circuits and the charge on the capacitor? Well, as the capacitor discharges, Q decreases, but that Q doesn't just disappear. That Q is the current. The current is the rate at which the charge changes, okay? And so the current is then just given by this formula right here. It's the derivative of dq by dt, okay? So if you don't know why, I mean, I kind of explained it just now, but go through the notes again and you'll see why, okay? And that's true not just for the RC circuit, it's true for all of the circuits. The current is basically the rate at which the charge moves, and so I is equal to dq by dt, like that, okay? So now you say, all right, well, great, how do I do that? Well, you're going to differentiate. Let me write that as d by dt, but what are you differentiating? Well, this whole thing, q. Maybe write it like this, hold on. d of q, and what's q? Q is this whole thing right there, like that, okay, by dt. And you say, well, how do I do that? I mean, you have to differentiate this, okay? And that's easy to do. It's not hard to differentiate, okay? So the first thing is that q naught is a constant, so it just comes out front, and then you get this piece in here, okay? And what's this? This is the derivative of an exponential. And you should know this. I mean, let me just do it off to the side here. See if you can see it. Yeah, you can. Okay. d e to the x, like that, divided by dx, like that. Or we could do t. It doesn't really matter what the variable is here, like that. When you differentiate an exponential with respect to t, it's just the exponential again, which is kind of the whole point of not the whole point, but that's one of the major properties of exponentials. The derivative of an exponential is an exponential. It's the exponential back again, okay? So when we differentiate this exponential here, okay, when we differentiate this exponential here, well, then we get the exponential back again. So we get that I is equal to the Q naught, okay? We get the exponential back again, but notice that the exponential has that minus t divided by tau, okay? And so you have to make use of the chain rule. First, you differentiate the exponential with respect to the entire argument. Then you differentiate the entire argument with respect to t. And when you differentiate that argument with respect to t, you just get minus 1 over tau, like that, okay? And this is basically, that piece right there comes out of the chain rule. Okay, so how does the chain rule work? Differentiate the exponential with respect to the entire argument, differentiate the entire argument with respect to t. Now, differentiating this with respect to t is easy because dt by dt is just 1, and there it is, okay? And then that minus tau, 1 over tau, that's just a constant. And so the answer is I is equal to, just put the Q naught and that together, and you're going to get minus Q naught divided by tau, okay, like this, multiplied by the exponential, like that, okay? And there you go. There's the answer right there. Okay, so if you actually do look through the notes, you'll see that that formula does appear in some form or another there. But I didn't directly, like you might not make on the test, you might not easily make the association that that is the formula for the current in an RC circuit. All right, let me see if there's any questions in the chat over that. And it looks like we're down to one viewer. Okay, so all right, there we go for that one. Okay, so now so that was for the RC circuit. Okay, what about an RL circuit? Okay, so what's the formula? Same kind of question here. What's the formula for the current in an RL circuit that is decaying? Okay, so the current now is going to be decaying, and that you could just look up as well. All right, so the current at any given time is equal to the whatever the initial current was multiplied by the exponential decay, which is e to the minus t over tau. And this time, not that we'll need it, but this time, because it's an RL circuit, the time constant is going to be L divided by R. Okay, so easy enough. Just if that's the question, what's the current in an RL circuit? You've got the formula, and I directly give it to you. Okay, both also in the non-calc notes. Okay, but now what if I ask this? What is the voltage drop? And I think I asked something like this in the in your assignment. Okay, what is the formula for the voltage drop across the resistor in an RL circuit that is decaying? You go, whoa, how do I do that? How do I get the voltage drop? Because I know the current, but how do I get the voltage drop? Okay, and it's across the resistor. Well, across the resistor, you say voltage drop across a resistor. What is there a relationship between voltage, resistance, and current? And the answer is yes. Obviously, it's Ohm's law. And so there you go. There is the voltage drop across the resistor. Okay. Now I wanted a formula for that, and so basically what I want you to do is all you need to do is like a time varying formula. All you need to do is take this, okay, and you say, oh, well, I mean, actually turn it around. Usually write IR, but we'll turn it around like that, okay? And now what's I? Well, I is given by this expression right there, you see? And so we can say that that's just going to equal R times this, like that, okay? And you could say that's the answer right there. All right, that was really easy, okay? So this is the voltage drop across the resistor. It's just whatever the current is at that particular time, which is given by this part of the formula, multiplied by the resistance. So the resistance multiplied by the instantaneous current will give you the instantaneous voltage across that resistor. Okay, and so that was easy or easy-ish. Okay, that formula is also in there again, but indirectly. Okay, now what if I ask this? What if I say to you, what is the formula for the voltage drop across the inductor in an RL circuit? Okay, and now you go, how do I get the voltage for an inductor? And it's equal to this. In fact, we had that formula above. Above, I had delta I divided by delta t. Technically, that's just average. Okay, it's just like velocities. You remember, like last semester, at the very beginning of last semester, we had average velocities and instantaneous velocities. So here, if we do di by dt, then you're really going to get your instantaneous voltage across the inductor. Okay, so the voltage across an inductor is equal to the inductance multiplied by the rate at which the current is changing. Okay, and you go, well, how do I do that? Well, now you've got this formula, but notice that you have to differentiate I. Okay, so and I is given by this. Okay, I is given by that. So you basically take this formula right here, differentiate it with respect to time, and multiply by L, and you'll get the voltage. Okay, so let's do this part here. Okay, just the derivative first. And so we're going to differentiate d of this entire formula here. Okay, let me space it out a little bit so you can see all the pieces. Okay, so there's the instantaneous current. Okay, and you take a look at this and you go, oh, that's what I have to do there is more or less what you had to do here, only now the role of Q or Q naught is replaced by I naught. So it's the exact same thing. All right. So what you'll get here is you get di by dt is equal to, pull out the constant multiplied by the derivative of just the exponential piece, and the derivative of just the exponential piece, because it's an exponential, is the exponential back again, okay, but multiplied by the derivative of the argument with respect to time, which is minus 1 divided by tau, like that. Okay, and you could just clean that up a little bit. Right? So we're going to put that constant and that constant together. Usually people put the exponential at the end, and so we're going to have this multiplied by the exponential, like that. Okay, and almost there. V is this. It's multiply that by di by dt. So now we have an expression for di by dt. It's this whole thing, like that. And just clean it up a little bit more. Let's put the L inside the whole constant there. So we'll get that it's equal to I naught times L divided by tau. Okay, there you go. Let me just space that out a little bit so you can see all the pieces. Okay, so here's the constant that's out in front. Space it out a little bit more. Okay, so a lot of spaces there. So it's I naught, the initial current, multiplied by the inductance divided by tau, and then multiplied by the exponential decay factor. Okay, so there you go. There's the expression for the voltage drop across the inductor, the instantaneous voltage drop across the inductor as this current winds down. All right. Okay. That's it for the lecture. And so you just have to be careful. In these problems, there's sort of the starting point, which is the kind of the bottom line, but then you could derive things from it, because you could say, well, is there a relationship between voltage drop and the change in the current? Okay, for the inductor, yes, there is, and that's what gives you this formula from this formula right there. Okay, and so that's one formula you're going to use. Here's another one you're going to use, which is Ohm's law, and here's yet another one that you're going to use right there, which is basically the definition of current. Okay, so given the sort of standard formulas, then you can derive the other formulas by either by using one of these three. Let me just write them down at the bottom here, using this one, or using this one, or using this one. Okay, you can start off with the fundamental formulas for the decay, but then derive some other electronic property from them using these three formulas right there. Okay, so there you go. That's it. Now, before the next test, I think I'll do a few more of these questions. I set the assignment, and then looking at it afterwards, I felt a little bit disappointed. I felt that maybe I should have pushed a little harder in terms of like different varieties. So, but there it is. Okay, so we'll practice some more of these before the final test. All right, let me see if there's any questions. I think there's only one viewer. Okay, so no questions, and that's it. End of the stream. All right. Good night, everyone.